morning, students. Wednesday, May 27th, 2020. Let's do a little earth science. So today I'm going to go through some vocabulary features related to groundwater. So I guess, as a learning target, what I'm looking for you to do is that you know and can define and use some of the terms related to groundwater. Okay? You might want to have today's little worksheet assignment handy as you're watching the video to help you fill things in. So let's talk about porosity. You've heard the word pores. You got pores in your skin. And if you think about it, pores are spaces. Okay? So when we talk about rock and soil, porosity refers to the space between the particles. Okay? And so there's two pictures here. You see this rock or soil is made of larger particles, and they only fit together so close, and there's spaces between them. Here's some rock or soil that's made out of a mix of particle sizes, and so in this case, the smaller particles fit in between the larger particles, which leaves less space for water. So porosity is referring to the space left over, the space that's available for water, or I guess in the case, it's not just water that gets stored in the ground. We have oil and natural gas and things like that that are stored in the ground. So porosity refers to space. This sample has greater porosity because there's more space. This has less porosity. So think of pores as spaces, holes. So the other really important word refers to permeability. If it's permeable, it means that liquids can pass through. So you have to have pores, but what if the pores aren't connected to each other? And I just thought of something I should have had handy for myself. Give me just 1 second. Okay, that was more like 10 seconds, but here's a piece of styrofoam. Now, styrofoam, as a foam, it's full of pores. There's lots of spaces. It's basically, bubbles wrapped in plastic. The thing is, if I put some water in here, that water will stay in there, virtually indefinitely, because the water can't move from one space to the next. The spaces aren't connected to each other. So while this is very porous, it's not permeable. Okay? Contrast that with a sponge like this. This is a sponge that's seen better days. But if I pour some water on here, the water moves through. And eventually the water is going to start to drip out the other side. The pores that make this up, there's lots of pores, they're connected to each other, and so the water can move through. So if fluids like water can move through the material, it's said to be permeable. Okay, and that word applies to our rocks. Permeability, the ability of water or fluids to flow through the rocks and soil because the pore spaces are connected. So here's a picture of a specialized type of paver stone that you could use if you were paving a patio or something. And they're pouring water on the top of it, and you can see the water draining through. The water doesn't just sit on top. Here's a plastic bag. There's water inside, but the water can't move through the bag. The bag is impermeable. So in order to have water held in the ground, we need space for the water, and in order for the water to be able to move around, it needs to be permeable. So the degree to which our soil and our rock structure below us is porous and permeable tells us a lot about what kind of water what water resources can be stored there. So the water that's held in the ground is called groundwater. Okay? It's held in those spaces, in those pores between the rocks. Okay? Now, the word aquifer, you hear that word, aquifer. It's referring to a body of permeable rock that contains or transmits groundwater. So if we went out, south of town and we talk about the aquifer, we're talking about this region of rock and soil that is permeable to water and it allows water to store and move through it. Now, some aquifers are connected to each other. The water can move from one to another, but sometimes there's layers of impermeable rock that separate one aquifer from another. Okay? So that's what defines where an aquifer is. If it's this region that's all interconnected. Okay? But it refers to that body of rock. This term could come anywhere in our water conversation, but a reservoir is a body of stored water. So a lot of times we hear the word reservoir when we put a dam on a river, and we dam the river, and so the water piles up behind it, forms more or less a man-made type lake. We sometimes call it a flowage here in Wisconsin. But that's a type of reservoir. It's a stored body of water. Well, an aquifer in the ground, if there's water stored in the ground, that's also a reservoir. So, if you went out in your yard and started digging a hole, and don't do that without permission, okay? But you start digging a hole, the surface ground is usually, maybe there's some moisture. We just had rain the last couple of days. There's going to be moisture there, but it's not going to be totally saturated, probably, depending on where you live. If we dig our hole, we're going to have this unsaturated layer. Saturated means the space is all full of water. So we're going to have a layer that's unsaturated, but eventually we're going to get down to a point where there is water filling all the spaces between particles. And that upper surface of that is called the water table. So below that is saturated. Now, depending on where, you may live in an area where the water table is right up by the surface. There may be some places where the water table, you have to go down several hundred feet before you get to it. Okay? And we humans have changed that. All right? I looked at some information last night about water table and groundwater, and one of the things it talked about is like in the region of the city of Chicago that has been using groundwater for the last 150 years, and their estimates are that the water table has lowered by something like 800 feet in places. Okay, where water used to be 800 feet higher, now you got to drill your well 800 feet deeper to get to the water. Okay, if we want to drill a well to get water out of the ground, we got to drill through this down into this area. Okay, usually we would drill a distance into this area so that our well has a reservoir stored in it, because if you just drill your well this deep and you start pumping water out, well, what if you empty this little bit out? Now you got to wait for it to fill back in before you have more water. So we like to have some extra storage capacity. The water table often somewhat parallels the Earth's surface. So if there's ridges and bumps on the Earth's surface, the water table kind of mirrors that, but it doesn't have to be a perfect match. Okay? So how does water get into the ground? Well, we have surface water, and surface water in places will soak through permeable soils and permeable rock and move into the ground. There's two words often associated with that. One is called recharge, because we're recharging the groundwater. Another word that you'll see is called infiltration. Yeah, sounds like something from some sort of a spy movie or something where, maybe you have a special agent who has to infiltrate a terrorist cell. Okay, what does infiltrate mean? To work their way into it. Okay, water is working its way into the soil, and we get into groundwater. So, recharge or infiltration is when surface water is moving into the ground, and then discharge is when we take water out of the ground. So in this case, I tried to draw some sort of picture that was representing a well, and we can pull water out. That's discharge. There are places where the water may discharge naturally. So a place where the water might get forced up to the surface, that natural feature is called a spring. And certainly we have springs around. If you are a kid living out in the country on a farm, you may have some springs on your property somewhere. And just because of the rock and soil structure, the water gets pushed up. Natural springs around the world have been a source of good water for a long, long time. Now, there's a lot of water down here. We said of all the fresh water on Earth, about 30% of it's in the ground. Here's the thing I want you to know. That water has taken a long time to get there. Sometimes you'll see the word fossil water. It's not an actual fossil, but it's just referring to something old. It's taken a long time for that water to build up in the ground. Now, if we poke a whole bunch of wells in here and start drawing out that water, we are discharging it potentially at a much faster rate than it's ever recharging. And that causes some real serious problems, or can. And there are parts of the world that are really dealing with that. Think about the city of Chicago again. If their water table is now 800 feet lower, and they're still trying to access that water table, to drill a well 800 feet is probably, I would guess it might cost $1 million to drill a well. Whereas, here in central Wisconsin, when I drilled my well, I think we went 160 feet, and it cost a couple $1,000. But, some of these wells, they're talking about $500,000, $1 million. That's a lot of money. So here's this diagram, just kind of, I'm trying to give a representation of Earth's water, okay? And so you know that the largest single part of it is salt water, right? 97.5%. So the rest, fresh water. Most of that's frozen in ice, okay? And then we have groundwater, which is about 30%, and this 1% is just surface water. So this certainly isn't to scale. But then I said, how does surface water show itself? Well, we have lakes, ponds, streams, rivers. Tributaries are little streams that lead into a river. Wetlands like swamps and marshes. The groundwater, you have your aquifers in the water, and so I listed some terminology with aquifers: water table, porosity, permeability. And then water can move back and forth between surface water and groundwater. If it's moving into the ground, recharge. Moving to the surface, discharge. And the entire area that's connected is called a watershed. And so there are areas of high ground that separate one watershed from another. One last little bit. So you and I, we all use water. And I want you to think about the importance of this water. So we all use a toilet. We are definitely contaminating some water there. Okay? We're adding some particulates and we're adding some biologicals. And what happens to that? So let's say in a city setting, what typically happens is that wastewater goes, let's say, to some sort of big tank, and it's just allowed to sit there and the solids from our waste settle to the bottom of that tank. So now we got another tank. We're going to take the liquid across here, and we're going to bubble air or oxygen up through it. And what happens is, see, there's lots of organisms in that wastewater. There's lots of bacteria and possibly parasites and other things in that wastewater. And so oxygen breaks those things down. And so, you bubble oxygen through here, and it's this big, really disgusting, bubbling slurry pot trying to get rid of the organisms. After that, we take the water over to another tank and allow it to settle again. Not quite sure why this stuff is coming up. Okay, so we allow it to settle again. By this time, the water coming off of here is getting pretty clean. So we might do, a final step. There might be some chlorine or ozone or ultraviolet light that's used to kill any remaining bacteria. And then this water goes right out, in the case of Edgar, Scotch Creek. And honestly, the water that's going out to Scotch Creek is cleaner than the water that's already coming down Scotch Creek. There may have to be some testing involved because there could be some chemical things. Okay, the city or village may have to add at some point early in the water treatment process, they may have to add some phosphorus. So then before it's discharged, you have to get rid of the phosphorus. So there are other steps. But these are the fundamental steps that go into most wastewater treatment plants. You have a settling tank, you have some sort of aeration, you have another settling tank, and then, possibly some final treatment. But when it goes out, this water is supposed to be clean. What if you live out in the country? You don't have a municipal system. So what happens is your waste gets pumped out to a tank, and again, in that tank, you're allowed to settle. And within the tank, this is the place where we want bacteria. Because bacteria over time break this stuff down. Then we're going to have a second tank. We're going to take the liquids across into the second tank. And there's a pump in here. And you have, possibly, this is the most common thing, you have a mound system out in your backyard, and this water gets pumped out into this mound system, where then it's allowed to drain down through a sand bed and down into the ground. Now here's the thing. There are bacteria and other stuff that's going to get out here into this. This sand bed works as a filter. And filtration isn't great at removing biologicals, but here's the goal. Here's the water table. You want enough height here so that as this water percolates down through the spaces, the further it has to go to the water table, the cleaner it gets. And so we want our system designed so that by the time the water gets to the water table, it's clean. And there's some engineering and science that goes into designing these things. And I think, overall, they have shown to be rather effective. Probably more effective than, in the past. Now, let's be honest. In the past, wastewater treatment plants were sewage. Let's dump it out in the yard or river. Just dump it without any treatment. So we don't want to do that. Okay, so I got some questions for you to answer again today. See you again tomorrow.